In this video we'll discuss the composite functions. We'll discuss what composite functions are all about, and I will also show you one example of a composite function. First of all, let's discuss the notation of a composite function. As you can see here, I have noted a composite function as f of g of x. The composite function is a function we create from two initial given functions, the function fx and the function gx. What we then can do is, if we combine these two initial functions, what will happen is that we will get a new function, the so-called composite function. The notation is exactly as we see here, f of g of x. What we have here is not a multiplication, it's simply f of g of x, or f circle g of x, which says that the function you will get from inserting g of x into the initial function fx. We can also create another composite function based on these two initial functions g and f of x, the function called g of f of x, and that function we get when we insert the initial function fx into the function g of x. So what does all this mean? Well, if we look at one example, it will make much more sense to us. So let's do that. In this example, which we will look at here, we will be given one function fx, which is defined as x squared plus x, and another function given by 4 minus x is called g of x. Based on these two functions here, f of x and g of x, we can create a composite function. And the first composite function we will look at is the function which we call f of g of x. And if you recall from the notation which we just discussed on the PowerPoint, what that means is that we insert the function g of x into the initial function fx. So that notation we can also write as f of g of x. Oops, we'll just delete this. Yep. And in this example here, where g of x is defined as 4 minus x, that will be equal to f of 4 minus x. So what is that all about? Well, if we remember what we discussed when we started discussing functions, then I'll just make a new color here to indicate that this is not something which is directly linked to what we're doing over here. But if you recall from when we started talking functions, and we maybe looked at a function, we could call that function fx is equal to x plus 2. And if we should then find a function value from when x is equal to, let's say, when x is equal to 3, how we found the function value was simply substituting 3 into the position of x in the expression for fx. So that must be equal to 3 plus 2, which of course is equal to 5. In exactly the same way over here, we would like to figure out what is f of 4 minus x. It's the very same thing. Over here we substituted the simple value of 3 into the initial expression of fx. Here we will substitute 4 minus x into the fx. So that is f 4 minus x must be equal to x squared, so x in this case is 4 minus x, so that is 4 minus x squared plus, and then plus x, and that is in this case 4 minus x. So now we can simplify this a bit by expanding the bracket over here. That is 16 plus x squared minus 8x, and then finally plus 4 minus x. So if we make this, we're simplifying a bit to make it nicer looking, then we see that the composite function f of g of x is equal to, what is it, x squared minus 9x plus 20. So now we have found the expression for the composite function f of d of x to be equal to x squared minus 9x plus 20. So a total new function we have seen here, created by the two initial functions fx and g of x. Let's also try to do the other potential composite function based on these two initial functions fx and g of x. So that's of course the composite function which is called g of f of x. That is the very same thing as we did when we looked at the composite functions f of d of x, where we inserted the initial function g of x into the function f of x. Then we over here insert the initial functions f of x into the function g of x. So that must be equal to g of f of x. And since f of x is defined by x squared plus x over here, that must be the same as g of x squared plus x. So let's see what that is all about. Gx is defined as 4 minus x, so altogether we have the composite function g of f of x to be equal to 4 minus, and instead of x here we substitute with x squared plus x, so that is x squared plus x. When we expand this bracket, we finally get that the composite function g of f of x is equal to 4 minus x squared minus x. So that is the expression for the other potential composite function g of f of x equals to 4 minus x squared minus x. As we can see already looking at the two expressions here for the two functions, these two functions are totally different. We can have, let's look at one example where we'll try to figure out what are the function value for these two composite functions when, let's say, x is equal to 2, just to illustrate also here that these two functions are two totally different ones. Maybe we have a bit more space over here. So when x is equal to 2, then f of g of x when x is equal to 2 must be equal to, and I substitute x with 2, so that is 2 squared minus 9 times 2 plus 20. And that must altogether give me 6. The function value for the other potential composite function g of f of 2 is equal to 4 minus, and I substitute x for 2, 2 squared minus 2, so that altogether gives me a function value which is minus 2. So we also see here that of course these two functions value will not be the same, because remember that the two composite functions f of d of x and g of f of x are two totally different functions. Alright, in this video we have only discussed how to compose composite functions, we haven't considered whether we could do it or not. There are some restrictions to when we can compose composite functions, and that is what we will cover in the video called Composite Functions Part 2.